video we're going to look at the next type of function, which is an exponential function. Now this type of function we've seen before, so it's a revision kind of exercise here, but just to practice some of the exam questions. And there's a couple of new little extra bits that I want to show you. So an exponential function is basically any function where you have a exponent or a power. So an example would be f of x is equal to 2 times x. That's an exponential function. Now remember, this could be written as y equals 2 times x. You have your input values and your output values. So this part here, the 2, is known as the base. And the x has 3 different names, which can make it a bit confusing, but it can be called the exponent, it can be called the index, or it can be called the power. Any 3 of those. I suppose you could say that exponential functions are written in the form f of x equals a times b times x. Now where did that a come from? Well, you could have something like this. You could have 4 multiplied by 2 to the power of x, or something like that. Now remember, that's not 8. You cannot multiply the 4 and the 2 to give you 8, because the 2 to the power of x, and sorry I've done that brackets wrong, the 2 to the power of x is, or the x is attached to the 2. You know your BIMDAS, you do the indices first. So the a and the b in this, the a and the b are constants, and it'll be like 4 times 2 to the power of x, or you could have 7 times 3 to the power of x, and so on and so on. There's lots and lots of them. You could have all those different values, but the a and the b are constants, and then the x is your variable. So we look at an example. We've seen these before, but there's a couple of little rules and tricks here that are handy to know. So these exponential functions, by the way, are very relevant today with what's going on with the coronavirus and COVID-19, because when we graph them, we get a graph that looks like this, where this is our kind of time. For example, if we're dealing with bacteria growth, and this is, let's say, growth. So what you find is when x equals 1, you get a low value. Let's say, for example, f of x equals 2 to the power of x. So when x is 1, that would be 2 to the power of 1, which is 2. So 1, 2. F to the power of 2 would be 2 to the power of 2, which is 4. So now we're going up to 2 here, but this is jumped to 4. F to the power of 3 is 2 to the power of 3, which is 8. So now we're at 3 here, but this is jumped to 8. F to the power of 4 is 2 to the power of 4, and you get what I'm doing here is 16. So when this is 4, this goes to 16. But what isn't clear on my graph, but hopefully you can see from the numbers, is that the jump gets bigger every time. When we go from x being 1 to x being 2, the output goes from 2 to 4, which is a jump of 2. When we go from x being 2 to x being 3, the jump is from 4 to 8, which is plus 4. Then we have plus 8. Next one is plus 16. Next one is plus 32, and so on. And this is known as exponential growth. And if something has exponential growth, it means that its growth rate is increasing. It's getting, not only is it getting bigger and bigger, but how much it's getting bigger by is getting bigger and bigger. And this is kind of very relevant with the coronavirus at the moment, because you'll see it in the news where if one person has it, they might give it to 2. But if 2 people have it, they might give it to 4. 4 people have it, they might give it to 8. 8 people have it, they might give it to 16. So not only is the virus spreading, but the growth at which it's spreading is getting bigger. It's spreading at a much, much quicker rate. So you'll see this, I'll make this a bit clearer when we go through some exam questions, but hopefully you have an idea that exponential growth doesn't just mean it's growing. It means that it's growing by a bigger amount each time. And that's why things like viruses and stuff, they can quickly get out of control, because it's getting bigger and bigger the amount it grows by. So let's look at a question involving bacterial growth. So bacterial growth can be modeled using the exponential function. The population of bacteria growth, P of x, so that means the amount of bacteria cells there are, is equal to 150,000 times 2 to the power of x, where x is the time in hours. Graph this function. So to graph it, or graph this function for the first 4 hours, so we need to find P of 1, P of 2, P of 3, P of 4, and I suppose you could find P of 0 as well. So you type all this into your calculator, won't it all? 150,000 times 2 to the power of 0, 150,000 times 2 to the power of 1, and so on, and so on, and so on. And when you do that, you should get answers like this table here. So when it's 0 hours, this is your output. For 1 hour, this is your output, and so on. Now the important thing to notice here, and this is a rule, if you have P of x equals 150,000 times 2 to the power of x, well, when you get P of 0, that means you have 150,000 times 2 to the power of 0. Now 2 to the power of 0, one of our rules for indices equals 1. Any number to the power of 0 always equals 1. So this section here just goes to 1, which gives you 150,000. Now that actually gives you a rule, and that rule is if you have a function f of x equals a times b to the power of x, when you draw your graph, your first output, your first y value is going to be a. And you'll see here when I draw this graph here, my first y value, when I draw it, when x is 0, y, my first y value is going to be 150,000. When x is 1, my first y value, or my next y value is 300,000. And so on and so on. Now when you draw the graph, and I won't draw it really accurately, you should get something that looks like this. I might draw it a bit bigger down here, sorry, it's messy. When you draw your graph, if your x values, your y values, you'll get something that looks like this. Now the shape of this graph is important as well, because what you see is the slope is getting steeper. And that slope getting steeper goes back to what I was saying there a few minutes ago about the growth rate is increasing. For the same jump in x here, you get a small jump in y. But for that jump in x here, you get a much, much bigger jump in y. And that jump in y gets bigger and bigger because that slope is getting steeper and steeper. So hopefully that makes a little bit of sense. I know it can be tricky to get your head around. So for the first one, I think you'll be okay with getting your points and then drawing a graph. Estimate the population size after 2.5 hours of growth. So estimated after 2.5 hours of growth. So what you'll need to do is you'll need to go to your graph and find 2.5 hours and go up and go across. And if you actually draw this graph, and I'd like you to actually pause the video now and draw the graph, you should get a value of the bacterial growth, the y value. Sorry, the pen is acting up again. Bacterial growth equals in and around, and it's an estimate, remember, in and around 850,000. And that's part 2. Part 3, find the exact population size after 2.5 hours of growth. So remember, when you're estimating, you're using the graph, but when you want to find the exact population size, you use algebra. So that's going to be our equation. So for part 3, we know our equation is P of x equals 150,000 times 2 of x. So we want to find the output when the time is 2.5 hours, so our x is 2.5 hours. That's 150,000 times 2 to the power of 2.5, and type that into your calculator and you'll get 848,528. So that's the actual, that's a 5, that's the actual number, and from our graph we estimated 850,000. Now you could have got 860, 870,000, it doesn't matter, it's your estimate. As long as that reads well from your graph, or as long as you've done the correct thing from your graph, you're okay. So I hope I didn't go through that graph too quickly there now, but do try and draw that. Number 4 then is the part that I wanted to kind of really go through that's new. Calculate the percentage error in your estimate. So we've come across percentage error before, but people tend to forget it. So percentage error is in a different chapter, but they do like to ask it with these type of questions. And if you want to find a percentage error, it is the difference between estimated value and actual value all divided by actual value. Sorry, the pen is getting worse and worse, but it's not my writing, I swear. Actual value all multiplied by 100 because it's a percentage. And what it is it's the percentage, how far out you are as a percentage. So in our case, I wonder if I change the thickness of this pen, will it make it better? In our case, it would be 850,000, which was our estimated value. Take away 848,528, which was the actual value, all over the actual value, which was 848,528, multiplied by 100 over 1, which equals around 0.2%. So our estimate was very good because it's not that far off, it's only 0.2% off.